obsłuży? Ja mogę zacząć pierwszą prelekcję.
Tak, Michał, zerkaj czasami i...
Bo ja to mogę zrobić na prezentacji.
Jest już jakieś pytanie, czy będzie po polsku?
Żebym nie musiał duplikować, mam tam zrobione tak, że wiesz.
Na tą prezentację mi styknie, a na tamtą będę miał ze swojego kompa.
Ale tak, ale no niech to będzie, wiecie. No możesz...
Okay, hello everyone. You're welcome on 32nd, I think, community Wrocław meeting. Where? Sorry. Okay. Hello everyone. Welcome on 32nd Wrocław community meetup, March of 2023. Thank you STGT for funding this event, for helping organizing it. Meet our sponsor, by the way. Okay, so everything you know about us, you can find on our webpage, raz-wrocław.pl. You can find our Slack link, so you can find our common community place to talk. There's our GitHub, so most of our presentations, materials, also something like that, you can find it there. So visit the page so you can be updated. We are community. There are two people, me and Michał, who organize this like daily, like gathering talks and so. But it's not always enough because we cannot do all the talks, we cannot do all the workshops. We need you to talk with us. And in particular, we need someone to help us with social media. So if you know how memes work, how to drive Facebook, maybe you can help us. So if you have those skills, please reach us either on Slack or catch us on integration after the meeting. But also we would really appreciate any help with giving you talks to all of you, because this is what you are. We share knowledge about trust in Wrocław. This is all I wanted to begin with. We do not have any kind of code of conduct. We're just nice to each other. And we want to start with Wojciech Razik, who talk about
some machine learning
models in Rust. So applause and
okay. Hello everybody, thank you for joining. Let me just switch the presentation. This is the one. Okay. Let me just test if it's worked correctly. Okay, not yet. Okay, so thank you all for joining. It's really glad to see so many of you here. Today, I'm gonna talk about some machine learning. So before we start, I just want to mention that this talk is rather dedicated to beginner level. So you will not find here so many advanced Rust code. I just wanted to show some interesting application that will use existing machine learning models, and I hope you will like it. Okay, so what is the current state of supporting machine learning in Rust? There is a website called arewelearningyet.com. You can go there, and the status is it's ripe for experimentation, but the ecosystem isn't very complete yet, and I think this is a true sentence. I will not recommend anyone to use it on the production. However, it was really a pleasure to play with it. Okay, so what is our motivation? So once every year, Wrocław University of Technology organize something called a team project conference. So we have, on one hand, we have companies, on the other hand, we have students, and companies cooperate with the students, and they can prepare some projects. So companies can find interesting students can learn how to work in like real environment. So in the last year, we have two interesting projects, and one of them was detecting the falls. And you can imagine we have some camera that is placed, let's say, in some elderly house, or maybe in some waiting room in the hospital. And based on that, we can inform proper people to help someone who fall. So use case is quite clear. I think that this application will be interesting. Okay, so let's start. As I said, we starting from the very beginning. So as you may know, the cloud is just someone else's computer, and AI is just a bunch of if statements. But what is the difference between machine learning and traditional programming? So in the traditional programming, we have some input data. It can be some images, it can be input files, user input, and so on. And we also, on the other hand, have set of rules. And our application combines these two things and creates some answers. In machine learning application, we need to learn using some existing data. So we are providing the answers and the input. And based on that, we create set of rules. And these rules can be later used by our application. Okay, I think more or less everything is clear because it's not a hard topic. So in practical application, we have this additional learning phase, training phase, in which we are preparing some model definitions. We are tuning these models. After the training, we are creating some artifact, some file that is described our training phase. And later on, during the interference phase, we can use it. But but what is hard about this training phase, it requires lots of data. And because it requires lots of data, it also requires lots of resources, lots of time, and of course, lots of money. So probably we don't want to use it. And instead, we want to use some existing model created by someone else, maybe by some big company like Google, and we can try to use it and build our application on top of that. So the real life application may look like this. So we have actually similar application in our company, one of the projects. So we are using some existing machine learning models. We have different set of such models, and we are combining them together. We are writing some glue to combine them, and based on that, we are preparing applications. Here is some like example chart with splitted face detection and pose estimation, so we can have multiple models that we can later use. Okay, I hope everything is clear. So short about me and the company. So I'm software developer since 2011. Most of the time I spend coding in C++. The people who knows me know that I'm big fan of C++ still. So I love Rust, I like C++, I tolerate JavaScript. But the most pleasant thing about JavaScript is that the moment when you're switching the language, that's my opinion. So I spent most of time during some telecommunication projects. I also did some computer vision on humanoid robot, face detection. Right now I'm doing software for vertical farm in STGT. You can find me on GitHub and on LinkedIn. I believe you can easily also find my email address if you want to contact with me. And our today's sponsor, STGT company. So what we are doing, we are mostly focused on embedded systems. We are doing lots of edge AI stuff. We are not only preparing software for embedded devices, we are also sometimes designing the hardware. We have some project related with IoT. So we started like three years ago. We have like 15 people right now. And our goal is to have some interesting project and innovative projects so we don't get bored at work. So, and we are using Rust currently in only one of our projects. However, we still looking for the place when we can put this Rust. Okay, so let's go back to the presentation. This is like obvious slide when we can use AI and machine learning, visual perception, speech recognition, subject detection, and lots of stuff. You probably know you have many things on your phones. So machine learning can help you with decision making, with anomaly detection, and other stuff like that. Maybe I will not focus on that. Why at the edge? So the ultimate goal for our product, so as I mentioned, it was fall detection, but not application that will run on PC, but instead we have dedicated camera, and this camera has NPU unit, so neural processing unit, a small chip that is dedicated to run machine learning operations, and our ultimate goal was to run it exactly on camera. I will show a picture of this camera maybe a little bit later, and why we want to use dedicated hardware. Okay, and why we want to use the edge, run machine learning on the edge. And the reasons are quite obvious. Lower latency, we don't need to waste network traffic. We can increase autonomy of the system. We are not dependent on any cloud solutions. Of course, the data security is better because we don't have to send our data in some places. And so on and so on. Okay, so let's continue. The other question you may ask is why Rust? Of course, because we can do it in Rust, so why not? Another reason is that I'm a Rust developer, so it's also a great reason to write it in Rust. However, I have one really practical example, because this application with fall detection was used previously. So my wife, she's a teacher, and in her school, it was event called Day of Science when I was presenting this Python application. So students wrote everything in Python. And I had big problem because this app crashes like every 10 and 15 minutes. So yeah, of course we can write better application, we can prepare more tests and so on. However, just because we use Rust, we cannot omit handling the errors. So I think it was like great motivation to write it in Rust. You will not have this all runtime crashes. You will maybe fight a little bit in the compilation phase, but it's still worth it, I think. Okay, now a few slides about pose detection. So we have different kinds of detecting the pose. So the pose detection will be used, of course, later by our application. There are a few types of pose detection. We have kinematic, when we just recognize key points of our body, and we can draw a skeleton based on that. We can have contour, we can have full volumetric pose. However, for our purpose, we don't need contour. We decided just to use the skeleton. Okay, so our choice was to use single pose to simplify a little bit. So yeah, just because we wanted to simplify, the beginning version of our application is able to detect just one person.
Wojtek, can I ask you for a second of technical break? There are some audio problems, and maybe you can. YouTube claims it's a bit too quiet.
Okay.
So YouTube, is it better?
Okay.
Let's go back to
okay. Let's continue. I hope now will be a little bit better. Okay. So we have different engines of pose detections. We have, let's say, Blaze pose, PoseNet movement. These are all pose detection models that are created by Google. This is not okay. I don't see this video here. That I was surprised. So we actually, our students tested many of them, and we choose 3 that was capable to run on this embedded hardware device. Okay, so we have Blaze pose. All 3 of them are from Google. And let's start with the first, the Blaze pose. So it is like strictly combined with Google's media pipe, and it was really hard to run it outside this media pipe. And it turns out that it was really slow. And we tried to make it a little bit better. We tried to do the quantization of the models. However, nothing worked. We either have very slow or very random data. So maybe I will give me a second. I will try to run it. So Blaze Pose is very accurate. It creates like 3D model of the data. So it's super accurate. It was super nice. We were very excited to use it. However, it didn't work. Okay. So then we have PoseNet and MoveNet. These are similar ones, so they provide the same output. They work very similar. Like MoveNet is upgraded version of PoseNet. However, we were unable to run MoveNet on our embedded device. I'm not sure how I can go into technical details. However, the machine learning model is like a graph constructed from TensorFlow population, because both machine learning models are TensorFlow. And some of the operations inside this model was not supported by our hardware, so we were just unable to do that. And we didn't want to modify the model itself. It was too hard. So on the embedded device, we use this PoseNet, and today we will use Rust to detect the position. So this is the camera that we will trying to run, and how our application will look like. So first, we need to grab some frames from the camera. We need to prepare data to the model. Model requires some specific data. I will show later which data are required. Then we want to draw something on the screen, and of course we want to detect pose. So we need to use some existing engine to do that. So we are using OpenCV almost for everything, and we are using TensorFlow Lite. So this is like a little bit different version of TensorFlow dedicated to run on the edge. The same TensorFlow Lite was used in Python application, and there is a library in Rust that binds C code, and it was nice and it was easy to use it. Okay, so this is how application looks like. This is fed by some video, so we can see that we are drawing the skeleton, and we are writing output when fall is detected. And on the next slide, is like in our office when I try to simulate the falls. Okay, so let's start how this application looks like. So the first thing we need to do, finally some Rust code. The first thing that we need to do is to read our model. So from the browser, we are downloading a TF Lite few megabytes file, and we need to open it with dedicated library. We are using a crate called TF Lite C, so C bindings of TensorFlow Lites. And we are creating a new interpreter that we will feed later with the data. So here we have interpreter new, so it's quite obvious. We also need to allocate tensors. It's like technical detail of how the TensorFlow Lite looks like. So it is needed for just to optimize the interference. So because after creating interpreter, we can put some other data, and we'll still, before using, we need to allocate it. It's boring stuff and easy stuff, as you see. Okay, the second part. Now let's start with camera stream. We used, of course, OpenCV, and it is, of course, possible to open just using integer number to run specific camera. However, the drawback is that it uses default settings. So actually, default settings are pretty bad, and adjusting it was not possible. That's why we decided to use GStreamer for that. So I don't know if you know GStreamer. It is using pipes that we are processing one by one. So we are opening video for Linux with our camera. We are using JPEG decoding, adjusting frame rate, width, height, and so on and so on. However, it works pretty well. And that's it. We have opened camera. Okay, so now we must fit our model. So when you reading details of the model, you can open the graph. However, there is also on the website information what's the data input. And in our case, MoveNet requirements are input is three-dimensional matrix, 192 by 192 by 3. So this is, of course, the square with three-dimensional RGB values. What is important, these RGB values must be floating point numbers. Hello. And output, we have 70 points, also three-dimensional, so X, Y coordinates and the confidence level. So how sure we are that this point is the correct point. Okay, so we will use OpenCV to do that. We have like two options. We can either resize and shrink the image, and we can crop it. I decided to crop it because why not? So we are at the top calculating how much we need to move our rectangle. We are grabbing the region of interest, so this ROI is region of interest. And later on, we're resizing using OpenCV. We are using algorithm called interarea. So this algorithm was supposed to be used for shrinking the image. So this is why I choose it. And at the last step, we need to convert integer values to floating points. Also, we have built-in operation. And great, really easy application. So what else left? Now we need to invoke our interpreter. So we are just copying bytes to our interpreter. And we are just reading the output and transforming it. Super easy. Okay, next steps, drawing the skeleton. So it is also like simple solution. I didn't want to show like full code because it doesn't make sense. This is, for example, how we draw the polyline using nice iter tools library, and we are creating like windows, so we iterate every two elements for some set of points, and we are using tuple windows for that. And the last thing is to calculate point position. So our machine learning model outputs values between 0 and 1, when 0 means top of the image, 1 is bottom of the image. So we need to also calculate and multiply by correct values. Okay, so we have skeleton, we are good to go. The last thing that left is how to detect the false. It is also like we did many experiments, students made lots of experiments how to calculate it, and we decided that we find first some point of the face, the best would be the center of the face. We will find position of our knees, and we are taking two frames, the first one and the second, and we are calculating the difference into separate frames. If this y value of this point shrinks, that means we fell off. It was working more or less. Okay, and this is example code when we calculating average of our face. Like we are grabbing some points. First, we are checking if they are above some specific confidence level, and then we are just calculating average of y, so center of our head. So, and actually it works well, because when you are standing in front of camera, the camera recognizes your eyes and ears. If you're staying like and watching side, they see your ears, and if you like back, they still see your ears. So it works in every position more or less. But it has also like drawbacks, so accuracy is so-so. We have many false positive. Let's imagine like we just bend over. It also detects as a false. However, it was really nice to play with that. Of course, lots of experiments needs to be made to verify our algorithm. And actually, it was like great reason to write some Rust code. And of course, this application needs calibration. So when we switching the camera, the values may vary a little bit, so we always need to adjust it. So what are the pros? We have something working. We have no runtime crashes anymore, and didn't require actually much work to do that. So I think it was nice to have it. But of course, that is not the full story, because we still want to benchmark, because we are using Rust. Rust is fast, so let's measure something. I hope you all, before any optimization, you measure your code, because it's super important to compile in release mode and benchmark everything and so on and so on. So measuring in Rust is quite simple. You can use some perf tool. It's a simple Linux tool, so you just need to update a little bit cargo. So here we are adding debug symbols to our release profile to see the stack. And we can run our code, and we see all of the CPU usage, almost all CPU usage was used by our interpreter. That is expected. However, I was playing a little bit with how the frames are calculated, and I saw that too much time we are spending on resizing the image. Okay, so I decided to make some additional measurements. So I decided to manually calculate the time of operation, and I use simple moving average, so I don't want to take all of the data but some specific range. I choose 100 frames to do that, and this is quite simple library. When you're just starting the timer, you're adding it, and at the end you have average from the last 100 results. And these were the results. So the cropping image wasn't time consuming, of course. Making floats also doesn't matter. The resize takes not too much for me, comparing to the invoking the full machine learning model. And heuristic also didn't take time. Okay, so let's back to our resizing image. So we used some inter-area algorithm, and it turns out, even though it's recommended for shrinking the image, actually it's really time consuming. So we just change it to something else. So the fastest resizing algorithm is linear approximation of the image. I will not go maybe into the details. However, after that, it turns out that the resizing now is 30 times faster. So it was for me, it was quite surprising, but this is how it looks like. Okay, so I think that would be it. To be honest, I don't think that machine learning frameworks are ready to be used in production, not in Rust. We are not there yet. However, I think in the future something may change. Rust is gaining popularity. So using existing models is relatively easy, and it's not cost us too much. So it was fun to play it. Writing custom heuristic requires really lots of testings, because the hardest part of this application actually was how to write proper algorithm to detect the false. So measure your code, because you can always optimize it somehow. And Rust is awesome, of course. Okay, but before we finish, I'm not sure if I can talk about it now, because we have some presents like STGT. So here on the screen, you are seeing Raspberry Pi Pico version with e-ink display, and this is prize for you. The first one who answers correctly for this quiz will gain the one reward, and after second tag we will probably play. So take your time. We know, Patrick. Maybe let's give it to someone else. Okay? No, I love Patrick. He's like the god of our Rust. So can you scream?
4, 4.
And the last?
4 and 4. Second one.
Yeah, the answer is 4, 4, and?
8.
No, incorrect. Patrick.
Oh, actually, I only talked about the first one.
Okay, the first one, so the same.
Yeah.
How about the second one? Any ideas?
0? Yeah, it's 0.
It's zero. But I believe the first answer should win the prize. Okay, so we will give it to a little bit later, and that's it actually. So about the usually we have Q&A session at the end of second talk. So
I mean, I think that it would be good time to actually
okay,
do Q&A for the first talk first.
okay,
And
I'm fine with it.
But
Okay.
also, right now we'll start Q&A session, and when there will be no more questions, we will turn off the stream. So if someone would like to ask a question which is not on stream, there also would be opportunity for that. But obviously it's better if everyone can hear an answer. So if you don't care this much about being on the stream, please ask the question. If there is a question, I have a mic for you. Okay, I will give it to you.
So on the slide that described the optimizations, the resize time went down, but the inference time went up. Is that something that
Yeah, that was
consistent?
random fluctuation
Oh,
of the data.
right,
So
okay.
I did many of measurements, and not always the invoke time goes up. So it
Okay.
depends on the size and how I was dancing in front of camera.
Okay.
When you were initializing this video for Linux video
Yeah.
capture, you specified the resolution there.
Yeah.
Couldn't you, instead of doing resizing, just specify lower resolution there and not do any resizing whatsoever?
Yeah, but then on the screen there will be like worse results. So
Ah.
remember, we still want to draw the image, but of course it's an option to resize first if we don't display. But I wanted to show you, so
Okay,
that's why I
see.
use full resolution.
Thanks.
Hello. So you are using, for example, OpenCV. So
Yeah.
it was written in C++, right?
Yeah.
So I also would like to ask what other technologies behind Rust, what other programming languages were used in this specific project? And did you measure how big was the binary? Also, how it weights everything?
The answer for the second question, no, I didn't measure. Actually, I was a bit disappointed that I was unable, for instance, to run our application on GPU because lack of support. So you have to remember that support for Rust for machine learning was really poor. And because OpenCV contains like everything that I needed, I choose OpenCV. We have like stuff in Rust that is able to draw something on the screen, but I decided to use the simpler solution. So the only Rust stuff is Rust and calling the external applications and so on.
Okay, I have a question. Is it worth to use JavaScript just to have this dopamine thing after you switch the stack later?
No. The real answer is no. It's not worth. It's never worth to write in JavaScript.
Okay, so
But I heard that there exist people who like the pain. They organize in some meetings and stuff, but yeah, maybe they are using JavaScript.
Okay, so we'll take some break. So please turn off the stream, and also before we go for the break, there is additional Q&A time.
raz, dwa, trzy, raz, dwa, dobra.
Powinien się nie poddać. Dobra, okej. To nie ten widok. Okay, we're back. It's loud. Now, okay. Is it good? YouTube, could you give me a hint if you hear us? Okay, so my name is Bartek. I work for Confio. I am maintainer of Cosmos, of Sylvia framework, and I would like to tell you a bit about internals of async, a bit about how runtimes for async work. So this talk would be fairly basic, but I assume you used async before. I will not go into details of usages, of what the async keyword mean, for example. So I assume your knowledge about usage of async, and I would like to tell you what you can expect about the underlying runtime implementation, for example, Tokyo. I will not do any Tokyo walkthrough because it would be pointless. Tokyo is very high-level thing and it is very complicated. It uses many optimizations. However, after this talk, I encourage you to download the Tokyo code base, to maybe take a look, because those basics I would talk about would actually be somehow implemented there. It would be just hidden a bit behind optimizations. Okay, so to understand runtimes and to understand the asynchronous execution, we would need four things. We would need the idea about what is the future, or in other stacks it would be promise, but this is basically the same idea. So we would understand how that works. We need to understand pinning on the very, very basic levels. What the idea of pinning is, and this thing is very rusty. It is not visible in other stacks. It is very, very Rust-related thing. It solves a problem which is not so difficult in other stacks. Then we need to understand waiters, and this is what I would start with, because this is the easiest thing to talk about at the very beginning. And at the very end, we need to understand the execution queue and the runtimes. So this would be the main part of my talk. So I told you that we need to start with waiters. And what I want to tell you about waiters is it is very important, and we will completely ignore this part. Why is it important? Because without waiters, the whole async idea has no point. So the thing is that without waiters, you will see in the examples I will show you that our runtimes would basically be busy loops. So they would eat 100% of your CPU all the time, which is not ideal. Waiters are the tools which allows you to integrate with your operating system, so you can like put your threads to sleep, and waiter would make sure to wake your thread up when it's needed. However, how it's implemented internally requires us to use unsafe, and it is very specific to the operating system. And unfortunately, I had to switch to some evil operating system for this presentation, different one that I used to prepare this code. And if I would, for example, use Linux tools to show you some waiters internals, I would be screwed right now. So I'm happy I didn't do that. Okay, so I'm done with talking about waiters. Now let's talk a bit about futures. And now I would show you some code. So what is a future? The idea of the future is that I want to give you something which would be there in the future. However, even Rust developers didn't invent time travel yet. That's kind of a problem. So we cannot give you something from the future, but what we can what we can do, we can give you some promise about something being available in the future. Right? This is why in many stacks you can find it called like promise, like in JavaScript. Yeah. But also in C++, I think. Yeah, I think. Anyway, so there are many ways how we can define the future, and here you see the implementation of the simplest future I could imagine actually. I mean, which makes sense, because, for example, the ready future would be probably easier, but it would do nothing. So how the future is defined? Future is a trait with two things. First of all, we need to define what type we promise you we will deliver in the future, right? So this yield now future would not give you nothing, but it would tell you I'm finished, right? Can you think about another future which has similar semantic, which doesn't return you anything but tells you I'm finished? I don't know. Sorry? Like sleeping? Timer, sleep, right? So this is something I would, but the timer, which I would show in a second, is kind of more difficult because it needs to check something. Yield now is the future, which first time it's called, it's not yet ready, so you have a chance to do all the other things you want to do, and the second time you try to use it, it would be ready. So it gives you one tick of your runtime to do things you need to do. And it's called yield now because if you think about asynchronous programming, when you use this await keyword, then you expect the runtime to hold up until the future is finished and take care about another things, right? So sometimes you may have kind of long-term task which do some things, but it actually never have a reason to break. But on the other hand, if you would create a busy loop, it would just never give a chance for your runtime to pick up another tasks, right? So because of that, there is this feature, which is called yield now, which gives you this single opportunity for your runtime to take care about all those pending stuff, and then when it's done, next time you can pick up another things to do. So how do we implement this yield now feature? So we have two arguments, and I would start with context. We basically ignore it today because context is related to what I taught before, so to waiter. And why would I use context? Let's say I have network connection, right? So what I can do is I can check in the busy loop if there are some data on my network socket, right? But it is kind of waste of my resources, of my CPU. What I would like to do is I would like to ask my operating system to ping me when there are some data on the network, right, or on my socket. I would like to call some blocking call, which would be, for example, select or appall syscall, which would block up until there are data on this socket. So context, the only thing which context provides me is actually this waiter utility. Because I don't want to go into OS specific stuff, I completely ignore this part. But the other thing I get is self, which is kind of obvious, but we have the spin we need to talk about in a second. So for now, ignore the spin and assume that self is just mutable self. Just for now, we'll come back to pin in a second. Okay, so what do? I check if I already yielded once, because once I want not to be ready. If I am not yet, if I already yielded before, then I tell, okay, now I'm ready. Now you can progress with my mind flow, right? But if I didn't yet yielded, then I store the fact that I just yielded, and I yield with pending. If we go into the poll, if we go into definition of pending, let's go to documentation. Just poll. Sorry, I had to switch to other computer, so I don't remember my shortcuts, but poll has two variants, just like option. It's just semantically something different. So it's either ready, so we have data to return, or we are pending, so yeah, there would be something in the future, because I promise you there would be something in the future, but there's nothing now. So then we are going with pending. In the past, when features were like in development, there were more there, that there were like, it was integrated a bit with error, but now it's very simple. Okay, so this is future, and this is fairly easy. This other thing is just sealed now, so I can call the sealed now future as a function, so it's a bit more handy to use, right? So this is just default constructor for it now with awaiting comment. Okay, but what is the deal with pin? So there is this problem. Like here you can see what is the future. Like yield now is a structure with some bool in there. So it is not a problem to move it in the memory. It's all fine if I move it around. I would return it from my function. All is fine with that. Nice. But note that my yield now function is async. And what does it mean it's async? It means that it actually returns a future which is generated by the language itself. It doesn't return yield now. It does return different future which is generated automatically by the language. I don't want to go into the exact ways how the return structure is built, but let's imagine that your async function contains some data on the stack, let's say, but it's not a function, so the stack is kind of, it has to be smart. So it has some strings, some data on the stack, but then it also contains references to this data. It borrows the data internally. And the future which is returned by this function has to keep this information about data and about references to those data, and it may happen that the internal structure which is created by async is referencing itself. It's self-referential. So, for example, I really struggle with the fact that I need to keep my mic, but I will handle that. Okay, I will be fine. So you can create a function foo. It would be async function. And here I would have, for example, have some it would keep the string. Oh, that would be, it would take the string by ownership, right? And then what I would have something like, I would say it's that, I guess. It should be okay, and it returns return my s, so it returns. It won't work. Okay, that doesn't s to owned. Sorry? Oh, I don't even need this return. I am being stupid. It happens. Let's call the to owned on that. And then I need to return the string. Like, this is actually pretty easy. This doesn't cause any problems for us because we just immediately call the function. There's no problem. But let's say some future which takes an s here, and I await for it. I do not define this future, but there is something happening which cannot return immediately. It may perform some I don't know, sending to the network, or it wants to do something with this data, so it has to be hold. Executor needs to pause executing this future. But on the other hand, we need to keep this s pointer to our original data, right? And then what would happen if I move the original data? We are screwed because original data moved. Actually, for string, it would not happen because string is kept on heap anyway. But if there would be something kept on the stack which moved, and we have the pointer for that, we invalidate our pointer. Is this problem clear? Yes. So what is a pin now? If I have pin over a pointer, that means I promise you this structure would never move unless it can. But I promise you that in the moment I constructed the pin, this would never move. There is one case when I can safely move pin, when it implements the unpin trait. So unpin trait means you can move it around. I don't care if you move it because I do not hold any internal references. So for example, this yield now future is unpin because I just have bool there. So if you move it around, copy to another memory, transmit to the network and then receiving it, all is fine. It works. There is the problem that if I keep internal references, I create futures which are not unpin. And then if I once pin it somewhere to the memory, I promise to the executor that it never moves. It will always be in the same place, so I can basically store things on the stack. This is for the compiler. And the funny thing about pin is that this is something you need to understand that happens. Sorry? The funny thing about pin is that as a developer, you kind of need to understand why it exists and what problem it solves, but I never had to think if some work is like stored in particular place in memory. You just need to know that if data are pinned, they are not moving and you are safe about that. I promised you another future, which is a bit more complicated, just to make sure that we are on the same page with futures. It's the timer future. So how I do I implement the timer future is basically the same. I create it with some time when it triggers. And on my poll, I do check first if time elapsed. And then when I should trigger, I just return ready. If I should not yet trigger yet, then I'm not ready. I would be ready in the future. Is the implementation of the timer future I provided clear? Okay, so finally I can move to interesting content. How are those futures executed? So I created 3 executors: block-on, single-threaded, and multi-threaded executors. And to be clear, none of them are working like Tokyo, because I wanted to make this understandable for people, right? But it should give you an idea how Tokyo roughly works, except it performs many optimizations. For example, it uses waiters, so it doesn't do busy looping, right? So my first executor is the block on executor, and this is very simple one. Let's go to source. It is like 36 lines of code including main, but it is like crucial to understand it. Because it like explains you how futures work. So let's start with taking a look at main. Main is a function which blocks on two futures. This async block just creates me a async context, so it creates a future from nom async code. The first future is just iterating 10 times, and every time it iterates, it yields me back, so I can perform some other tasks. For block on, there are no other tasks, but I want to perform this yield now, and I print some number, and then I execute another future, where I wait for 2 seconds, and then I claim I never more need to wait. So this is what I want to do. Let's verify that it works. I should build it on the machine before, so it's cached, but it doesn't matter. That might be maybe a reason, actually. Let me save it. Yep, and let me rebuild it. Yeah. So you are like pretty nice helper here. Did it wait for 2 seconds? That's the question. Yeah, it does some waiting. So I just proved that I have something which works. Let's take a look how it works. So block on is like very simple executor, which just do not exact. It doesn't have to be busy looping, but it waits till the future is done, and this is all it does. Here I need to create a waker because I cannot work with async without waiters. It's impossible. But let's start with the spin mode. So I have some future taken as an argument, and as you remember in the future like poll method, it takes myself by pin. Doesn't matter if my future is unpinned or it's not unpinned. It doesn't matter. It has to be pinned to the stack when I call it. So not necessarily to the stack. It has to be pinned somewhere. So first I use the pin mode macro from the futures crate. It's helper for working with futures, which pins my future to the stack, and it would be pinned forever basically. Then I create waker and nope waker also from futures task. This is waker which does nothing. This is like the trivial waker implementation which never wakes you up. It doesn't let you to subscribe or nothing. It is just, I need to put something in my context basically. I also never use context, so it doesn't matter what I put there. And then what I do, I have like infinite busy loop, and all the time I just call poll. And when it's ready, I return the value. So, any questions? So thank you, I'm done. I mean, this is how executors work. Except, I have problems here. I mean, it works, nice, but there are many things I cannot do, because this is synchronous programming right now. But I want to be asynchronous. So what problems do you see, guys? And ideas, what I can't do, which I would really wish to do? Why program asynchronously?
You don't really have access to the underlying asynchronous facilities from the system, so you cannot like asynchronously call a socket.
I can. I could block on socket write or socket read. It would work. But let's say I kind of can. I can create future which selects on futures, which like right on with them, but I cannot spawn futures. So what I really like to do when I program asynchronously, I would like to create a task in the background which I don't poll myself, which is just polled. And I do not need to await on this because I just want to have I create my TCP server, right? And I just want to have this, let's call it thread, which listens on the pod, and if someone connects, then it spawns another thread, which is not a thread, it's a task. But it's kind of a thread, and I don't await on this. It is just polled somewhere in the background, and when it's done, and I don't care about the result, right? So this is what I like the most, and I solve it in my single-threaded, version of the executor. Let's run it. First, let's see my main function. Or that would be more interesting to start with my main function. It is a bit more complicated because I want to utilize my spawn utility I created. I would obviously go for the implementation. First, let's see the effect. So I use this helper function printn, which is just a loop which prints a string n times and yields every time it printed. So it can, take care about tasks on the background, right? So this is the implementation. I put a string and then it prints me the string and which iteration of the string is it. Okay, pretty simple. Then yield now. So first of all, execute is my block on, but it's called execute because it's never more block on. And it takes a future which it awaits finalization. We'll see it in a second. So how does it work? Here, I just want to print next 10 times. Here I want to wait for 2 seconds, exactly same thing, because we want basic example first, but here I have new thing. So I create 2 futures. First would be printing foo 10 times, and the second would print bar 10 times. And they are returned, but I don't wait on them immediately, except I would await them at the very end, right? So first, let's start with running the code. Waiting, okay. And what you can see here, it is exactly overlapping. I mean, though the first part is the same what was before, it is just to show you that not too much changed. But here you can see that those foo and bar, it's not like multi-threaded. In multi-threaded environment, it would be somehow chaotic. Right here, I have just this loop which goes through all the features which are spawned, and then it executes them. And what's very important, you will see that the features that I'm polling there are not those features, because those features, this F1 and F2, are polled here. I'm awaiting them here. But what is spawned is different feature. We'll see it in a second. What I want to show you is what is the last thing. Bar is printed the last. I would comment out this await. So here's an interesting question to you. If and what if something would change on the output if I comment out the second? It is kind of guessing because you didn't see implementation yet, but you can deduce it, I think. What and if something would change if I do not await on second? It will. It will. But is there anything more? Because as you can see, I don't necessarily care about warnings in this example project. No.
No, we won't see the last bar because we are not awaiting for it.
Exactly. What happens is both features are polled in round-robin fashion, but when my main feature, which is this async block, we have 3 features here. We have our main feature, main async feature. We have F1 feature, which is spawned, and we have F2 feature, which is spawned, right? And the whole execute function would break execution when the main feature is done. This is my, and then when F1 is done, because I wait on the F1 handler actually, not F1 itself, but on its handler, then I am breaking the execution and the last bar should not be printed. If it is, then I'm lying, but we finish on, we are unlucky. Did I save it? Okay, it's, I mean, I have an idea why it could not work is because it's not very predictable. It is kind of predictable. Yeah. Sorry?
The round robin part, maybe.
Yeah, the thing is that, let's see that if I removed both, the reason why it didn't work here, the exact reason is that after F2, I mean the whole main feature is pulled after the F2, probably. Yeah. This is how it's scheduled. So F1 is done. We don't await, but then there's F2 and that's delayed. But
Yeah, so if you increased F2's number from 10 to 20,
yeah,
we wouldn't see the remaining.
Yeah, that's good. That's what I can show here. Oh, 50 doesn't matter. Good point, Patrick. Thank you. You can see that now. Exactly. I commented this guy, and now it happens. I should remove the weight. Exactly what happens. You see that this bar printed even one more because it's kind of predictable, as I said, but it is precisely predictable, but you would need to think about it deeply, how it works. But you can see that
there's also third execution variant in here. If you uncomment both F1 and F2,
nothing shows.
Yeah, if you uncomment both, so the way it started, but you don't use spawn, you just assign the future directly to both.
Then they will be sequentially done. Yeah. So that's what would happen with you, which is kind of seen like here. I could just go with. I really don't want to do this typing with one hand, but yeah, exactly how Patrick said. If I would just do those print instead of doing spawn here, I would just do print and full blah blah dot await twice. It would first print all fulls, then print both bars. And now let's go take a look on the executor. This one is a bit longer. How long? Almost 100 lines of code. The last one is 1,000 lines of code. So I hope you have whole night for us. We have we defined this thing which is called future plus static. I don't want to put this everywhere. So if you see future, it is just dynamic future which is static. So I can spawn it. And I have an executor. I call it executor context, but I really would not want to use the context word because context is something else in Ising. And I have this queue of tasks in my round robin. So my round robin is doing, full cycle through tasks, and I am single threaded, so I use refcell for that. This is just a vector which I would access dynamically. All of those are pinned boxes. I do it for simplification because if I use box, then I use something on this heap, so I can just pass the pointer and don't care about data being actually moved. So I will be able to very easily pull those futures. And there is a few, so it's dynamic future. And the question to the audience, why I have split it into tasks and spawning instead of just having one tasks and push things to the end. I know, Patrick, that you know, but anyone else know? Patrick?
Because futures can call spawn only when they are executing, so they cannot. So you cannot use the same variable because it's locked when the future is running. Exactly,
because the spawn would be called in the futures. Yeah, so I would not be able to push something to task. So what I do here, let's take a look at the easy sum function first, the spawn function. What I do in spawn function, I create a remote handle. So what is remote handle? I it is from the future tried, from future X actually from the future library. It is not anything very complicated, but it just makes it easier for me. I create two futures. And one future is basically copy of myself with a little bit of boilerplate. And the other one is a future which would be finished as at the exact same time when the other one. So I can pull one future and I can await on different future and have this like relation that when the one is done, then I can signal it on the other one. So why I do it? Because the remote function, the remote future is something I would like to add to my spawning thing. So my spawning are features which I want to spawn soon, whatever soon means. We don't know what soon means yet. But the handle, I want to return something so you can await on this. And this is, you can think of it like about join function in your thread. Like you can join on this future, so you want to progress only when it's done on some fictional thread. Nice. So we are we have this spawn which basically enqueues a future on the spawning vector. Think of this vector as a list. Now the execute, the core part of this. So now we need to be careful listening. We have IDX. I don't want to use iterator here for many reasons. Mostly because I don't want to keep any borrows to my tasks between executions. So I just use index of next future to pull, right? I create my wake, this is yada yada yada, nothing relevant. And now I have busy loop. I am single threaded, I have busy loop. And I need to, sorry, I think I missed one thing. Oh, here, very important thing. How I create my task and spawning. So at the very beginning, my tasks is a single task. The task I am created with on this execute, right? So I create a single vector with a single remote boxed future. This is my task and my spawning is empty. So at the very beginning, I have only single task. I want to pull it. You can see I use this remote handle to keep the handle for future verifying if the future finished, right? And here is kind of a trick. I want to move things into my closure here. In particular, what I want to move here, I think I want to move my handle, but if I use move here, I would move this exec. And I don't want to move this exec into the closure, so I can basically shadow my exec with the borrow to itself. So I move only the borrow internally. Executor set is just utility from what I use here, which is called scoped thread local. Scoped thread local creates me kind of static variable, which is local to the thread. Here I have only a single thread, but what is very nice about scoped thread local, it's not exactly static. It alives only in this closure. You see, this closure of exec set. So what happens in exec set, I initialize my static variable, my global static variable, and when I leave this closure, the static variable never exists, never more. But I need it to be global so I can create the spawn function, basically. I would like it not to be global, I would like it to be in my execute function, this whole thing, this executor, but I need access to that from the spawn function. So here in spawn, I call this with closure, which would fail if I am not in this whole set context, right? I mean, that's the whole idea of that. So here I start my executor by creating my execution context. I pass the execution context here. I set my index to 0 because I need to pick something, and 0 is the only index I know I have. And then I need to poll my future. Here, I poll my future. I know there are many calls in the between, but what I do here, I have tasks. I need to access them mutably because I need mutable access to the future because it may modify itself. I access the index, take a smooth, I poll, and I need to know if it's ready or if it's pending. Why do I need to know if it's ready or if it's pending? It's not the last feature to execute. So why do I need to know if it's ready or pending? I need to know because if it's ready, I never more can poll it. It's by definition, I cannot poll future which returned me ready. It's in the documentation. So what I do here, if it's pending, I just increase the index. If it's not ready, I do swap remove. And this is also why it's kind of not exactly predictable, because I do not, if future finished, I do not just remove it, I do this swapping, because I don't want to have any guarantees about ordering. I don't care about this. I just want quickly remove something from the queue. And then tasks. Here what I do, I checked my output, so I increase my index, and after every future I executed, I need to add all the futures which were spawned by it to my task queue. I couldn't add it immediately while it's executed because of this borrow mode basically. So this borrow mode locks my thing. What I want to do is here I just add them to the future, right? And I'm using this drawing thing. This basically adds items from one vector to another, leaving the other vector empty. And last but not least, I need to figure out if I want to stop my executor. How do I figure it out? I check if my handle, what is my handle? Handle to the original future is done, right? And then at the very end, I do IDX modulo len, because it may happen that, I mean, I want to be very much safe about not indexing something on the scope. So at the very end, I am just cropping the index to length of my futures. Basically, in the case, it removes something. Is this clear how the single-threaded executor works? Because it was actually the most difficult thing in my presentation. The multi-threaded is actually simpler in terms of if you understand this, you should understand the other. I assume no questions means it's okay.
I do have one question. Instead of doing this match on the 59th line, couldn't you as well just check if it's poll ready when the index is first? Because this would be the first spawn future, the root future, and then return if that happened. So, you know, if index is 0 and the future is poll.
Probably yes, and then I would not need to use this split. Here, I didn't want to do this because when I was first creating it, I was considering using the circular buffer, and then it would possibly make it a bit more difficult. But yeah, in this case, probably I could use that, but I didn't try that. But probably you are right. Okay, multi-threaded. The last one, and as I promised, it is 1,000 lines of codes, right? As you can see, it's the same length. I promise you it won't be this difficult. Let's take a look at main. It's very, very similar, but I changed one thing in this last execution. Let's take a look first on this print n. Additionally to what I printed before, I printed on which thread is this executed to show you something about how it works. So it is exactly the same, except I just additionally printed thread ID I'm executing on. We may want to increase those for presentation purposes, we'll see, but I do not spawn 2 futures, I spawn 10 of them. So it is a bit more chaos for presentation purposes, so I need to await for all of them. It should not be too complex. I didn't remove the slip, so we have 2 seconds of waiting. But let's take a look at the terminal now. So what happens? We have those prints like really unordered right now. See, it's we have 10 tasks which are randomly printed. As you can see, orders are increasing in terms of single task, but it's not exactly like increasing. 2, then 3rd, then 2nd. It's like one task is getting ahead of another task. It happens. And then you can see that here, for example, thread 10, whatever it is executing task 3, task 7, task 0. And then task 0 here is first executed by some kind of thread 11, but then by 10. So it's messed up. Which thread is it? Threads are not tasks in us. Sometimes they could be, often they are. So it's often for optimization purposes done as long as it's possible. Single task is executed on the single thread. We try to do that because it's often more performant, but it's more difficult to implement. That's why I didn't care if this implementation. Let's take a look at the implementation. Feud got another trait, which is send. I need to be able to move my future between threads because you've seen, it's once executed on one thread, on another thread. I need to be able to shuffle my future between threads. I doesn't have any context like executor because my context is way simpler right now. Before my context was 2 queues. Right now I just use slice of sender, boxed slice of sender, so vector of sender. What is sender? Do you know MPSC utility from standard thread? I am not talking about any kind of Tokyo magic. Standard library, single producer, single consumer. So what is it? Patrick? Okay, MPSC, yeah.
Multiple producers, single consumer, right?
So what? Yeah. So what is it for? Channel. Okay. I just wanted to make sure that it's not just you are sitting and you blindly listening. Okay, nice. So basically utility. So there is a queue in the memory. So I can put something there on one thread, and I can pull this thing on the other thread. The only limitation is that there can be only single thread which pulls things. But there can be many threads which pushes things. And here, because it's scope thread local, every thread has this own set of input pipes. So every thread has one output pipe which it pulls from, and every thread has all the input pipes for all the other threads, right? This is how it's organized. I need my next sender being globally accessed because there are many threads, right? And I want them to run it, to push it to the queues kind of fairly. And there is something that it's very difficult in multi-threaded programming to decide how to kill threads. It is a thing. So there is this done flag, which is atomic bool. When it's done, all threads are finishing after next future they poll. This is how I manage. And now threads is just a constant, so I need to decide how many threads I execute. In more serious environment, I would detect how many calls I have and so on, blah, blah, blah. Here I just spawn 4 threads. So first of all, how do I spawn feature? Exactly the same how I spawned features before, except it's a bit more boilerplate. So I have this remote handle. I would use handle to return it at the end so I can pull it easy. Here I need to do something with senders, so senders is my context here. And first thing I need to do, I need to figure out to which queue I need to schedule things, because I want to do some basic load balance. I want to always push to another sender. So I do, next sender is atomic integer. I just need to increment it. I just do incrementation, and this whole thing just makes sure that it's done atomically. If it that happens that some other thread did increment it at some time, it would try it as long as it would help. We don't care about any memory barriers right now. That's why it's sequential CST, because we don't want to care. So I have my next sender. So what I do, I push my future to the next queue. It's scheduled for execution. And then execute function. It is a bit more complicated, so try go step by step. First of all, when I start executing, I am not done yet. Right? Second of all, I need to figure out, I need to store something in next sender, and the question to the audience, why is 1 not 0? Because my executor would push my initial future to the 0 queue, so I want my next spawn to push to the first queue. I don't want to overload the first queue at the very beginning. It doesn't matter, technically, but, you know, I want to be fair. I create remote handle to my main future. I create like 2 vectors of senders and receivers to the channels. So this, for as many threads as I have, I create a channel. A channel is a sending pipe and the receiving pipe. Sending pipe can be cloned, receiving pipe cannot be cloned. And then I unzip it, so instead of vector of pairs, I have pair of vectors. Sorry. And then I make sense into boxed slice, so I have a little less overhead than having a vector. This is micro optimization, which I should not do for presentation purposes. And then for every receiving handler I have, because I have as many receiving handlers as threads I want to create, for every handler I have, I spawn a thread, right? The executor thread. This is actually executing thread. I need to create waker and context, so yada, yada, yada. And then I set my context for this thread. My context for this thread is senders, but I clone them. So every thread has its own set of sending pipes. I clone them. And then what I do, in the busy loop, while not done, now it's not infinite, now it's while I'm not done, I poll my future, right? This, I check, I try to take some next future to execute from my queue, sorry, and then I poll my future. And I check if it is not pending, because right now, because I am not having like one single vector and going through this, I'm just taking the future, trying to execute it, and if it's not done, I just push it to the queue. This is not the best implementation, it's the most naive implementation. I just create this, so we have couple queues, and my executor, my main thread of my executor just takes next item, pulls it, oh, it has to wait, okay. Push it to some other pipe and take another thing. And this is how executors work. This is basically how Tokyo works, how async works, except they're more fancy about waiters, they're more fancy about micro optimizations and so on, but this is the idea. Last thing, I need to break my executions at some point, right? So when I spawned all my 4 threads, I spawn them, I need to send my initial future to the 0th channel. I drop sends, which I don't need to do here, but it is a very good idea because sometimes you want to break your thread where all senders are alive. And it hit me that I forgot to drop the sender on the executor thread, so it is always alive, and my subthread never ends. So I find it being a good habit to drop your senders when you never more need them. Not necessarily here, but good habit in my opinion. I create a waker for my root thread, let's say it, and in root thread, the only thing I do, I just check in busy loop if my main feature is done using my, and here trick which Patrick suggested won't work because here my main feature is shuffled between threads, so I have no like magic access to it. I really need to use this remote handler. Okay, so that's all. I really don't want to go into details of waiters because we are pretty long here, or an hour. one of my longest presentations, so sorry for that. I hope it was understandable. My question is, are there any questions about this? First, online questions, and then we would go into offline questions. I can take questions in Polish, by the way. I speak English for our audience, so it's understandable on YouTube, but if you are not comfortable with asking in English, it's okay. Question?
So you said that you also studied the code of another like libraries, Tokyo, etc. What was the optimization that you liked the most or surprises you the most in those libraries?
I don't know. Is there any optimization which surprised me? I think that maybe it's not something which surprised me or I like the most, but it's the most important because it defines the idea of phasing. Is basically that you in Tokyo or in other runtimes, instead of having busy loop, I mean you would have this busy loop, but on the very end of this busy loop, you will have syscall like Apple to your operating system, which basically sleeps your thread up until whatever is registered to this EPOL is finished. So this what this EPOL basically is, what this EPOL is kind of, in Linux is basically file descriptor, which is related to as many file descriptors as you would like to. So you can have 1,000 file descriptors connected to it. And when you try to subscribe on this file descriptor, when any other descriptors related to that would be ready, you would be notified with the information which one is ready or which one are ready. And you also destroyed my final question. I would figure something out in a second. Okay, there is a question. Could you go with Mike on the very end?
Yes, so I'm curious about the state of the function which is being suspended when we call await. It needs to be stored somewhere, as far as I understand the async mechanism. And can you tell me if I understand it correctly, or if so, where is the data stored?
So basically, you'd like it to be stored on the stack, but practically it's often stored on this heap. But the optimization for that sometimes. But the question is how it's done. So normally in this async functions, you do not have like very regular call, but you can think about that. There is created the intermediate representation, intermediate structure, which is often a kind of an enum, but not an enum.
And it's created by the compiler, right?
It's created by a compiler. And how it looks like, how I like to think about that, because it's not literally how it looks like, but I like to think about that every await is a variant in this enum, which contains all the stack up until this point.
Yes, and this
then
stuff
after
needs to be stored somewhere, right?
On the heap, or here. It's where it's okay. It's stored in those senders, in those MPSCs. It's easier seen in the single threaded. Though those futures are those states. Those futures are structures created by us. If you would see here, sorry, very sorry. So print line is async function, right?
Correct.
Which means if it could be kind of written as this, then here impl future output being this. Kind of, because if I would do that, I would not be able to use await. There are tricks for that, but yeah. So this print n, it returns me this fake enum created by compiler, which I then pass to execute. I do not call await here. So what I pass to execute is this artificial future type.
All right. So we basically have two types of futures. One which we can create via implementing the future trait, and there are also these compiler-generated futures which are generated automatically for each async function which actually awaits.
They are basically the same. It's just the thing is that there are things we cannot write literally in Rust without unsafe, self-referential structs in particular, and that's why also if you would ever on the recruitment procedure and you would meet me on technical interview, I may ask you if async is just a syntactic sugar. I like to ask this question because it is not. If it would be, it would not allow you doing anything like unusual, but it actually allows you to doing self-referentials, which you cannot do without it. So, yeah,
Alright.
this is the question I like to ask.
Okay, thank you.
Okay, other questions? Okay, I will go off stream. Could you go off stream here? Maybe, sorry, if you didn't left yet on the stream, we will do an off-stream session in a second, but we want to ask a question for the audience for prize, and we will do that on the stream. So I cannot that simply ask on what to use for using synchronizing system. What funny thing did I use on the presentation? I would ask for. Yeah. No, just give me a second. That should not be too difficult. But I would like to ask you why. Okay, I would like to ask you why this thing has to be pinned. Why this has to be pinned? I will briefly talk about this, like with a single word, an idea, and I know Patrick, you know that. Sorry? Yeah, exactly. That was that simple, because I have to be sure that if my poll function, uses any references potentially in my structure, they point to proper places. Okay, so thank you all. Don't go offline yet. I would like to say hello to everyone watching us on YouTube. We will see each other hopefully in this month. We will announce details on our Slack probably, also maybe on social medias. And really, if there is someone who would like to help us, especially in social media, but also if there is someone who would like to give some talk, we would really appreciate your help, because I can talk every month. But do you want to listen to me every month? I bet no. So, yeah. Thank you very much, and
big thanks to organizers to the ISA, to the students, to our audio guys. So thank you for helping with organize this event.
Okay, and the word for CEO of STGT, our sponsor tonight.
Okay. Hi everyone. I would like to thank you for joining us this evening in this beautiful place. The Rust community is growing rapidly, and what can I say? We are happy and proud to be able to support you. Enjoy your evening. Thank you very much. Thank you for invitation, Bartek, Michał. We are waiting for the next one. Thank you so much. Enjoy.
Thank you very much for doing this stuff, and I hope you would have some cooperation in the future. Thank you. Now we can go off stream.